to kick off the chlorine. Which gives us this acidic amine, but then the Cl minus or base you threw in if you had to, can pick out this protein proton. To give us our M. Plus HCl. And so there's an equilibrium for this reaction. And it's going to favor the amide because HCl on the leaving group Cl minus is more stable than the nucleophile, which is an ammonia. And so we can really quantify a KEQ. So the KEQ based on comparison of the pKa's. So the conjugate acid of this is a pKa of 10. For the conjugate acid, or Ca. And then the HCl is the conjugate acid, but HCl is a pKa of 0. So then the KEQ, you can think of it as the pKa of the less stable thing minus the pKa of the more stable thing. So 10 minus 0 is 10. So we can basically think the KEQ of this is 10 to the 10th. So 10 to the pKa1 minus pKa2 is going to roughly give us an idea of what the KEQ is. So in this case, it would be 10 for the pKa of the ammonium, which is the nucleophile. So pKa of the nucleophile minus the pKa of the leaving group of the conjugate acid, which is Cl minus or HCl or 0. So the KEQ for this reaction is going to equal 10 to the 10th. So it's going to completely and utterly favor the formation of the amide. And you can tell this because of the difference in the pKa's. Yeah.
Okay. I'm so lost because last semester we learned it as conjugate acid minus acid. So 10 to the conjugate acid minus acid. So I thought of it like...
So that's a memorization. I'm really doing the exact same thing.
Okay.
Trust me, I'm not changing anything. I'm doing, and this is a different reaction too.
Okay.
You're talking about acid-base.
Yeah.
This is where it's the equilibrium between an acid and its conjugate base. I'm not talking about the same thing, which is what that's talking about. This is talking about two different species. Yeah. Yes.
So what I see is like the HCl is like a very strong acid, while
But it forms HCl in the last step. In this step, right, it kicks off Cl minus. And so the conjugate acid, and so it's what's going to be more stable, Cl minus or Nu, which in this case is ammonium.
what would stop the HCl from then repropagating via B and like then having that and kicking it back off?
Well, it absolutely can, but then what I just said was then it can. And how many times did I say this reaction is completely in equilibrium?
Yeah.
But the KEQ is favored by 10 to the 10 because the conjugates, because ammonia is a lot less stable than because the ammonium is 10 orders of magnitude less stable than HCl. So HCl is 10 times more acidic, which means the conjugate base of HCl is 10 times more stable than the conjugate base of ammonium. So another way to think of this, because pKa's and nucleophilicity are inversely correlated. So another way to look at this, equilibrium is going to lie on the side of the weaker nucleophile. And the weaker nucleophile is going to have the lower pKa. Right? Because if you have a lower pKa, you're a more stable conjugate base. And if you're a more stable conjugate base, you're most likely going to be less nucleophilic. Yes?
So along those same lines, since the pK of ammonia is like 10, but HCl is like 0, wouldn't it exist like 10 to the 10th in the favor of the protease amine as opposed to HCl at the
Yeah,
end.
but the HCl doesn't form at first, right? When you take the reaction, you have amine plus carboxylic plus chlorine.
Right.
And so we were just talking about that. And yes, this does generate HCl. And you bring up a great point. I was just trying to, illustrate this chemistry we'll talk about. In general, when an acid chloride, because of what you just suggested, you need to add in a couple equivalents of a base to soak up the HCl. So you usually have something like pyridine around. Maybe I chose a hard introductory, I think I probably chose a hard introductory example. But this is the same thing though. So pKa's, I'm asking, the stronger acid is always going to, the equilibrium is going to favor the stronger acid. Let's just leave it at that. The equilibrium, what's the stronger acid, the nucleophile or the leaving group? And the equilibrium is going to favor the stronger acid. Let me show you another example. This is good though. This discussion is great. Thank you for everyone who's asked questions. So if you take acetate or some kind of conjugate base of a carboxylic acid, it will add in an acid chloride, giving us a tetrahedral intermediate, and then kicking out the Cl minus to give us our anhydride plus Cl minus. So in this case, I just got rid of the pesky proton. So if you take some kind of carboxylate, so the conjugate base of a carboxylic acid, and it adds into an acid chloride, gives you your tetrahedral intermediate, and then kicks out Cl minus, that gives us this. And so the conjugate base, the conjugate acid of Cl minus is HCl, so that's a pKa of 0. The conjugate acid of this is a carboxylic acid. What's the pKa of a carboxylic acid? About 4.5-ish. So if we take the 10 to the pKa of the nucleophile minus the pKa of the leaving group, that'll be 10 to the 4.5 minus 0, which means the equilibrium will lie on this side of the KEQ of 10 to the 4.5. Is that more clear? Is that a clearer example than this was? Because I can definitely lead with this in the future.
Yeah.
Yeah, someone raise their hand? But, so is it, yes?
I was going to say, can we just have like the nucleophilic attack and then have the chlorine leave, or do we have to show all 4 arrows?
Oh, you have to show all 4 arrows. If you don't, that's still kind of You have to show me and show the graders that you actually do understand that we are getting a tetrahedral intermediate, but we can't be bothered by drawing the tetrahedral intermediate for chemists, and we know the tetrahedral intermediate is going to form. Yes?
That sodium just counteracts the chlorine.
Oh yeah, well
right?
yeah, of course. NaCl, table salt. Yeah.
So if we write the whole intermediate, would it be wrong?
If you wrote what?
The whole intermediate?
Oh no, good for you. More power to you. I'm just a lazy chemist who doesn't like drawing tetrahedral intermediates unless I have to. Yeah. Well, so when we talk about the, well no, the pKa of Cl minus is not 0, but I said the pKa of the conjugate acid of Cl minus, which is HCl. So I think what's kind of confusing us is I was saying the conjugate acid of this. So maybe I should just get rid of the pesky conjugate acid and just say, you really can't when you have 2 nucleophiles, but we're talking about, so once again, the equilibrium is going to lie on the side of the weaker nucleophile. And nucleophilicity correlates with pKa. All right, so the lower the pKa, so a pKa tells you how stable the conjugate base is. So the lower the pKa of a conjugate acid means its conjugate base is going to be more stable. And so if a conjugate base is more stable, it's going to be likely to be less nucleophilic. So that way we can use that back of the envelope logic to explain why the equilibrium, basically we want to say the equilibrium is going to lie on the side of the weaker nucleophile swimming around and the stronger nucleophile forming a bond to carbon. The equilibrium is going to lie on the side of the weaker nucleophile swimming around in solution and the stronger nucleophile forming a bond to carbon, the carbonyl. All right, and a quick and probably the easiest way to explain, well, what's a stronger nucleophile, what's a weaker nucleophile, is comparing pKa to the conjugate acids of the nucleophile. Because acidity, pKa, is a measure of the stability of the conjugate base. So the more stable a conjugate base, its acid's going to have a lower pKa. So pKa is just a nice, easy way to help us rationalize what's going to be a better nucleophile or not. So, is this case clear? This is becoming clearer now. I know I may have muddled through it, and I probably should have led with this example, not this amine example. But let me go to the amine example now. Now that we've talked about this, I'm going to re-go through the amine example, okay? I care too much, right?
I think
What?
people are probably getting hung up on, like in 232, it was explained like, you never form the strong acids. You don't form strong acids. They all, give off their proton.
Yeah.
So
Yeah,
I think that's what.
okay, and so it was my fault for not including a base. Or a lot of times you might add two equivalents in the amine. So one of the equivalents adds in the amine. So let's do that. Let's do two equivalents of the amine. And then you can replace the Cl minus taking the proton with a second equivalent taking the proton. And so then we form the amide plus the second equivalent taking becoming the ammonia. And then we also have Cl minus. And then we can compare what's a more stable conjugate base, Cl minus or, so does that make more sense? All right, did I go through this? Yes.
So, but see, this one this one totally makes sense to me because there's just Cl minus floating around.
Yeah.
That's like a gray. I can see that
Alright.
definitely wants to be formed. But the HCl, you're saying that is totally viable and that's totally.
Oh, so I just changed it. So.
Yeah. But
So in general, if I have any problems, I assume everyone is thinking what I'm thinking.
okay.
You can ask some of my students. It drives me crazy sometimes. So you usually have to have some base around for an amine to attack an acid chloride. So just to show you something, if you have an extra equivalent of amine, one equivalent's going to attack. It's going to give us this. It's going to kick off Cl minus. And it's going to give us this ammonium. All right? And this is the book's nomenclature. I would probably have the other equivalent of amine take this proton, but the book has it take the proton here. So I'm going to stick with the book to not confuse anybody. But so it attacks, and it can kick off this or this. Since this is 10 times more stable than this conjugate base would be, it's going to kick off Cl minus, giving us Cl minus plus this protonate amide, and then this number of electrons is going to go and grab the protons from this, giving us our neutral species, ammonium and Cl minus. And now the thing we're trying to compare is what's more stable, amine, tertiary amine, or Cl minus. And then the way we compare this is we take, well, the conjugate acids of each. One is HCl, one's ammonium. HCl is 0, ammonium is 10. So that means by 10 orders of magnitude, chlorine's more stable, meaning the amine is roughly 10 orders of magnitude, 10 to the 10, more basic and hence more nucleophilic than the Cl minus. And so the equilibrium is going to lie towards the stronger nucleophile, the amine, forming a bond in the carbonyl, and the weaker thing, Cl minus, swimming around. So is that better when they add a base? By the way, thank you for catching that. You don't know how great that makes me feel that you guys not only didn't let me go on, you stopped me and you rebelled, and that's exactly what we need, right? You guys, I hope it was a learning experiment. I almost wish I could say I did it on purpose. But great learning experience, right?
Yeah.
All right, so in general, what time is it? All right, I have 2 minutes. And so pretty much acid chlorides, which we talked about, any nucleophile will add into an acid. Because can you think of a lower pKa thing than a Cl minus? You can't. But that led to the question, how do you make an acid chloride? How do you make an acid chloride? Because if we do any of this nucleophilic acyl substitution, we have to find a leaving group that's a better leaving group than Cl. And that's going to be awfully hard to find or make. So the way we make acid chlorides is we take a carboxylic acid, and we take a reagent that's a sulfur double bond to an oxygen, and there's 2 chlorides off of the sulfur. So this is called thionyl chloride.